Hello everybody, and welcome to another assembly tutorial. So we're going to continue on our little excursion into structures and classes today. But first of all, I just want to say that I've updated my little website, and I'll put the link in the video description, so go over there and the slides will be up probably by the time you watch this. Yeah, it's got a lot more stuff there now. I'm going to start putting music there and Android apps and some Windows apps. Anyway, go and check it out. Okay, so C++ classes and assembly. There's actually no object-oriented programming in assembly. It's not an object-oriented programming language, but C++, as we know, is. So we're going to have a look today at exactly how that actually works. It's a combination of a few things. There's structures, there's name mangling, and there's an implicit pointer parameter, the this pointer. Yeah, so we'll have a look at it. Member variables first of all. So the member variables of a class are actually just a structure. Static variables are a little different. We'll have a look at those at the end, but the normal member variables are just a structure. So once again, we've got to define the structure in assembly along with the class's declaration in C or C++. We've got to define it in assembly as well. And remember the data packing trick, the pragma pack, push, pop, whatever it was from the previous tutorial. Yeah, we've got to have C++ packing the data exactly the same as assembly, so we use the same trick. Yeah. Okay, so here's a bit of an example. Yeah, I think we'll write something like this at the end of the tute. Yeah, so you can get a good view of exactly how it all works. But pragma pack push 1. That's just to make sure that C++ is packing data exactly the same as assembly. And my class is just a simple vector class. It's got two floats, x and y. And this over here would be the assembly structure for the same thing. So we know that assembly is going to automatically pack things, aligned to 1 or not aligned at all. So the assembly structure for the same class has no functions at all. It's just got the data, x and y, and they're both real fors. Real for is the assembly equivalent to a float. Good stuff. Okay, so the methods of a class are actually a trick of name mangling. The names of the methods are mangled to include information about, what the class is, and how many parameters or what the parameters are that are being passed to the method, and also the return type of the method. And once again, for a complete description of name mangling, you'll have to have a look at Agner Fogg's optimization manuals. Number 5 actually has the information in it, but we're going to use a little trick. Yeah, name mangling is very complicated, and we don't need to know it. So have a look there if you're interested. But I'm going to show you a trick so we can get around it the easy way. Here we go. More often than not, you don't need to use the mangled names, or you don't need to know how they're constructed, because Visual Studio is going to tell us what it's looking for. More precisely, it's the linker. The linker is going to give an error. If you define a method's prototype in C++ and you never declare the body of the method, if you try and call it somewhere in C++, the linker is going to give us an error. And in that error, it's going to say the exact mangled name that it's looking for. So we'll have a look at that at the end, but that same trick, getting the mangled name from the linker, we'll use time and time again in this tute. Okay, parameter passing. Parameters are actually passed using the C calling convention by default. There's no C++ calling convention, it's just the C calling convention. So parameters are passed in exactly the same manner as we're used to. RCX, RDX, R8, and R9, or XMMO, XMM1, XMM2, and XMM3. And the slide will tell us mangled names for any procedures, not just class methods. Oh yeah, so just incidentally, this has got nothing to do with classes or object-oriented programming, but if you'd prefer, you can just say, instead of using xturn C all the time, you can just say something like void some procedure and then int ABC, and then copy the mangled name from the linker. Yeah, and declare that in your assembly file instead of xturn C on everything. I'm not sure how the how the linker finds it when it's not declared as external, but it does. Okay, moving on. So the this pointer, this is really important. There's an implicit operand to the methods of a class, and it's the this pointer. Yeah, it's always passed as a first operand in RCX, and you don't usually, specify it when you're calling a class's methods, but it's there. It's being passed in RCX as the first operand. So that means that the actual first operand to the method, so we've got a method that maybe takes two integers, a and b, the a will be passed in RDX, since RCX is used to pass the this pointer. Or if you're passing floats, then XMMO won't be used at all. The first float parameter will be passed in XMM1. Okay. Yeah, and then it goes on to use the stack after that, after XMM3 or R9, it uses the stack as per the normal C calling convention. Okay, the new operator. Before the body of the constructor is called, if we've defined the body of a constructor in our assembly file, like we're going to do at the end, the new operator will already be called, and the new operator, thank goodness, will allocate the memory for us. It's already going to have allocated the enough memory on the heap for the structure, all of the member variables. So we needn't allocate that ourselves, and by the time the body of our constructor is run, we'll already have a pointer to that memory in RCX, the this pointer. Yeah, good stuff. The new allocate, yeah, you've only got to allocate extra data. So just as in C++, if you've got a class that has sort of dynamic memory associated with it, then you've obviously got to allocate that yourself using malloc or whatever you want, and then deallocate it in the destructor. But usually the new operator takes care of the normal member variables. Okay, so the delete operator is pretty similar to the new operator. It's going to deallocate the structure's member variables itself. We don't have to do anything. But by the time the body of our destructor is called, it's going to be just before it does that deallocation. So the this pointer in the destructor is going to be passed in RCX as per usual. But, it's going to be just a perfectly alive, normal structure. And then straight after our delete function runs, the normal member variables will be deallocated by the delete operator. Okay, static variables. So there's also static variables in classes, and you can define these in assembly or C++ if you like. They're a little different. They're actually just global data, so you can define them in your data segment. But they've got mangled names. Just like the procedures, they've got mangled names. So once again, the linker will tell you what it's looking for, only if you try and use it in your C++. So static variables don't form part of the actual structure, and they add nothing to the size of. You might have noticed in C++, if you take size of and then you define 20 static variables in your class, size of operator is going to return exactly the same size. You needn't mention them at all in your assembly structures definition, and the linker is only going to tell you the name it's looking for if you try and use the static variable in C++ somewhere. If you just have the declaration in your class, your C++ class, but you never try and use it, the linker is not even going to care. It's not going to tell you what the name it's looking for is. So yeah, it's best to write a little temporary function that uses the static variable in your C++. That way you can copy the mangled name that the linker is looking for from your error window. Okay, static variables. Here's just an example of the static variable. So we've got pragma pack push 1, set up the data packing, even though in this example it doesn't actually matter. And my class called static example has one static integer called j, and I've just got one little function called getJ. And over here in the assembly we can see one really important thing is that you've got to mark at the top of your assembly file, you've got to mark that the mangled name, that's J right here, that's the that's the mangled name of J. You've got to mark that it's public. So at the top of your assembly file you put public, and then that name there I copied from the linker, or the error window. Down here we've got the actual definition of that variable. It's dd, it's an int, and I've just set it to 29 for no real reason. But right here we can see the name mangled function as well, that returns the variable j. It's exactly the same as a normal function pretty much, only we've got to use these awful names. Yeah, so we just move that variable there, which is holding 29 at the moment, into EAX, and we return it. That variable there, there's only going to be one copy of that. Obviously, that's a global variable, perfectly normal global variable, and yeah, that's exactly what static variables are. Okay, so access modifiers. Yes, a big part of object-oriented programming is these access modifiers. And you might have noticed that on the previous slide we actually accessed a private member variable. I mean, it wasn't a member variable, it was a static variable, but it was marked as private. So usually in C++ you couldn't do this, but ASM, assembly doesn't care about that. It's interesting also that C++ really doesn't care either, and it's pretty easy to access private members from outside of a class, so long as you know whereabouts they are. So right here I've got a little example of that. We've got private int x, and I set it to 5 in the constructor of my class, but then in the main method, it's easy enough to access that integer if you just use a pointer and dereference and reference a few things. Okay, good stuff. So that's the end of the slides, and we'll do a little example in a minute, but I might just pause this and I'm back. Okay, so we're back. This is C++. We're going to make a little vector class and define all of its member functions in assembly. Include IOStream, as always, using namespace std, just so that we can print some stuff out and make sure that it's all running as we want. Class, we'll call it vector2. Oops. Oi. Yeah, that's better. And we'll say public. I might say here there's we'll make them floats. X, Y. Okay, so we want a constructor, vector2, and it takes float X, float Y. We want a destructor, vector2, which doesn't take any parameters, and float get X. Might make a getter for the X value, and float get Y. Okay, so that's our basic little vector class there. I should actually put up here pragma hack function1. Oops. There we go. Just make sure that C++ is packing things properly. Pragma pack pop, and make sure that it's packing things normally again. Not that it matters in this example. Okay, let's see what happens if we run. Oh, nothing. Okay, so I've already added the assembly file on that, and now what we've got to do is actually instantiate one of these. So vector2 v, and we'll say maybe 1.4 and 5.6. Actually, they better be floats, just like that. Then we'll try and print them out. It's v dot get x and v dot get y. And all. I'll save that and stick a breakpoint there. Okay, so we've pretty much just defined a little vector class and we've tried to use it, but we've not defined any of the bodies of these functions here. So we're going to do that in assembly. If we come over here and just put an end there first of all, .code, and we try and run it, it should whinge. Okay, we say no. Okay, so down here in the output window, I can see the linker errors. The first one at the top here, it's saying that there's an external symbol unresolved, and this is actually the destructor. I can see that it's the destructor. I don't know how clear this is on the on YouTube, but I can see that that's the destructor. So right here you'll see a very strange string. It's going to start with something like question mark 1, vector 2, and then at. That's the mangled name there that the linker is looking for. So if we just select that and we say copy, then we come here to our assembly and paste that right there. Proc ret and p. There we go, my friends. That's a constructor. It's going to stop whinging about the constructor now, and the linker will be perfectly happy with that. If you'd allocated stuff in your dynamic memory in your class, this would be where you free it again. But we haven't, so let's just keep moving on. Okay, so the next one that it's whinging about is get x. What I might do actually is copy the constructor first of all, and we'll do get x and get y after. So the constructor I can see is this one. I just copy the mangled name from the linker's error window, proc ret and p. Okay, so like we said, the constructor will already have called the new operator, and we're going to have a pointer to the RAM that it allocated in RCX by the time that we get here. And all we've got to do is move the parameters in, so that's this 1.4 and 5.6, move them into that RAM, and then put the return pointer, that's the this pointer that we were passed in RCX, into RAX. But I just realized that we didn't actually define our data. We didn't actually define our structure, so vector 2 struct, it's got x is a real 4, and we don't care what it's set to, and y is a real 4, and we don't care what it's set to, vector 2, and s. Yeah, we've got to make sure that we define the structure in our assembly file as well. Anyway, so the parameters will be passed to us in xmm1 and xmm2, since the first parameter is the invisible or implicit this pointer passed in RCX. So we're going to get 1.4 in the low float of xmm1, and if we mov ss, we've got d word ptr rcx dot vector 2 dot x xmm1. Okay, so that's the x value, and we're moving that into the new this pointer that the new operator allocated for us, and likewise we can do the same thing for dword ptr rcx and vector 2 dot y xmm2. Okay, so the x value from the constructor's definition will be passed in xmm1, and the y value will be passed in xmm2. And the only other thing that we've got to do is mov rax rcx. So move that this pointer into rax for return. The constructor always has to return the pointer to the new object. Yeah. Okay, so that's how you make a simple little constructor there that sets up two floats. Okay, so we've got two other little functions here, but I might just run it and see if we've got any problems so far. Nope, seems good. Okay, so we've still got get x and get y to define. They were the other two functions. So let's do those. Once again, we just copy straight from the linker's error window. And I might put these underneath. Okay, so here we've got the get x procedure, and if you want to return a floating point value, you do so in the low d word, or the low the low float of xmmo. So once again, when we get to this is a member function, and the this pointer will be rcx. So all we really want to do is mov ss xmmo, move a scalar single into the bottom of xmmo from d word pointer rcx, and that's a vector 2 dot x. Yeah, so that's going to move the x value of the this pointer that we were passed into the bottom of XMMO and return it to C++ whenever we call getX. And the other one that we've got to do is almost the same thing, only that's getY. So we'll just copy the mangled name from the linker once again, proc ret and p, and this is the same, only instead of .x we're returning .y. If I just save that and hit run, let's see what happens. There we go, 1.4 and 5.6, which is exactly the x and y values of the class that we set up. Yeah. Okay, so I hope that was a good example, and I hope you get the hang of it. It's pretty interesting stuff. I don't know how useful it is. Yeah, but it's really interesting stuff. It might be more useful later on when we get onto, or if we ever get onto array of structures versus structure of array. You know, setting up data in order for SIMD to access it better. But yeah, it's really interesting information anyway. So, hope you found that useful, and thank you for listening.